Hi, and good evening if you're in my time zone, or probably good morning for many of you there as well, depending on where you are. So yeah, my name's Falk Scholer. I'm from RMIT University in Melbourne, Australia. Sorry, Zoom has just put up some message for me. Anyway, dialog box accepted. Thank you to the BHCC organizers for inviting me along to give a talk here. So this symposium is, of course, about biases in human computation and crowdsourcing. And so what I'm planning to talk about for the next 15 minutes or so is some research work that was carried out in the context of evaluating search engines, and in particular around measuring a concept that's used to evaluate search, namely relevance. But the main focus of this talk is going to be on how crowdsourcing was used, and in particular, how it was used to capture human assessments using a rating scale that's very different from traditional ordinal scales that most of us know about. And we'll also consider data quality and whether our human crowd workers were able to carry out the task, or if we just collected random noise. So relevance is a fundamental concept in information retrieval. It tells us whether our search systems are achieving their aim, which is to help a user to fulfill an information need, right? And how do they do that? Well, they try to return relevant items in response to a user query. So in addition to being an important concept in information retrieval, relevance is also a complex concept, and operationalizing it is still not as well understood as we might like. So, for example, we could probably think of many different attributes that might make a document relevant for a searcher. For example, the first one is topicality. So this is asking whether the returned document is about the same topic as the query that the searcher issued. Another one might be novelty. So is this document presenting additional information, or is it just repeating things that the searcher already knows about? Context could be important, and that could include things such as the complexity of the document and its readability level. A searcher might be interested in or reflect on how authoritative a document seems to be. So does the information appear trustworthy or not? And even people's existing beliefs could have an impact, right? And whether a document seems to align with those or contradict them. And potentially there are even many more dimensions to relevance. However, in information retrieval evaluation, these relevance judgments are typically only made using the first of these, which is topical relevance. This is also called aboutness a lot of the time, because in essence, it's answering the question, is this document about the same thing as the query that was entered? And so why don't we measure all of those other aspects? Well, in the IR domain, a key consideration is that when we do these relevance assessments, we want to make them as reusable as possible. And arguably, all of those other dimensions are more subjective than topicality. So we'd hope that in many cases, if we ask two different people to say whether a document is topically responsive to a query, that they might more often than not be able to agree on that, whereas a lot of the other dimensions have personal aspects as well. So in terms of measuring this thing called relevance, then typically this is done using an ordinal scale, and essentially that means that we have ranked categories. And so we can say that one category is higher than another or lower than another, but the distance between those isn't specified. And historically, relevance was assessed just in a binary fashion. So a document was either judged to be relevant to a query or not relevant. But as you probably all know from your own searching experience, most people can differentiate much more nuanced levels of relevance, right? You might sometimes get a document back and you look at it and go, great, and it answers everything you needed to know and you're done. And at other times you might get a document where you go, oh yeah, this has some interesting stuff, but I'm going to need to look at further documents to actually complete my quest of whatever information I'm looking for. And so relevance over time became more formalized in terms of these graded ordinal scales, or in other words, ordinal scales with more than two levels. And one well-known example is work that was done by Eero Suominen and his colleagues from Finland. They carried out a study where relevance was assessed by a team using a 4-level scale. And that's the second blue box on the slide here. They named the 4 levels explicitly, and from lowest to highest, they are not relevant, marginally relevant, relevant, and highly relevant. And in addition, they came up with quite nuanced and specific definitions for each of these. So for example, there are some very specific features that make a document highly relevant versus relevant. But of course, if we decide to move on to graded relevance, some additional considerations arise. So one of them is, how many levels of relevance should we have? So Sormanen and colleagues chose the number 4, but other people have used 11, 21, 101. So the final blue box here is an 11 level relevance scale. And of course, a second issue that arises after you've considered how many levels your scale should have, and that is, are you going to label each of these levels and try to provide a careful definition of each one, such as Sormanen and team did? But as I'm sure you'll appreciate, even for this 11 level scale from 0 to 10, we probably wouldn't want to have to create explicit named labels for each level, or moreover definitions. So another option is you just label the endpoints. So here it's not relevant through to highly relevant, and then you let people choose on a numeric gradient. Now, alternatively to ordinal scales, we could use a completely different approach. For example, magnitude estimation. So this is a scaling technique developed by Stanley Stevens, who was working at Harvard in the 1950s. So it's been around for quite some time. And Stevens was working in the domain of psychophysics, which is the study of the measurement of perception. And in essence, this process of magnitude estimation works as follows. Stimuli are presented to a participant, one at a time, and each stimulus is at a different level of intensity. And a participant then assigns a number to reflect their perceived intensity of each stimulus. So, for example, they assign an initial number, which is called the modulus, to the first stimulus that is presented to them. This number is somewhat arbitrary. It's just a starting or anchor point. And then subsequent numbers are assigned based on the perceived ratio of intensity. So suppose a participant is being asked to create a scale to reflect their perceived loudness of a sound. They might arbitrarily assign the number 10 to the first stimulus they hear at some volume level. When the second stimulus is presented, if they perceive the sound to be twice as loud, then they would assign 20 to the next number because that's twice as big as the first number. And so you can keep going and you assign essentially numerical ratios to reflect how your perceptions differ. All right. And so initially magnitude estimation was developed for physical stimuli, such as the brightness of a light or the frequency of a sound and so on. And these things have an underlying measurable quantity. And Stevens, as well as other colleagues before him, noted that there's a remarkably stable relationship between how people assign these numbers and the underlying quantity. And the particular strand that Stevens, I think, pretty much pioneered was to also apply this then to other areas where there aren't physically quantifiable stimuli underlying it. So, for example, magnitude estimation has been used to create scales for levels of pain or emotional stress in medicine, to assess perceptions of the severity of crimes, or conversely, the appropriateness of punishments in the legal domain, and perhaps closer to our purposes, to establish scales about the usability of an interface in human-computer interaction, or to judge the grammaticality of sentences in linguistics. So let's have a quick go at magnitude estimation. So we're going to create a measurement scale for our perceptions of brightness. You're going to need to prepare a mental notepad just to store a sequence of 3 numbers, so it's not going to be too challenging. So in this first step, just choose a number as your modulus or your starting point for how bright this ring is. And note that you're not trying to estimate the brightness using some existing scale, such as Candela. It's just an arbitrary starting point. All right, so I'm sure you've all done that. Now here's stimulus number 2, assign a level of brightness to this, and remember it should be in proportion to your previous. And here's a third stimulus, so now assign mentally a brightness number to this one too. And congratulations, you've now created a magnitude estimation scale for the brightness of the one ring to rule them all. And hopefully the score that you assigned for the second stimulus was lower than what you assigned to the first. And most likely the third stimulus will have received the highest number of those that you assigned. And so if you haven't come across magnitude estimation before, you may be wondering, okay, so what? Why are we doing this weird complex thing when everyone knows how to use a simple ordinal scale? Because we do that all the time, right? Assign things from 1 to 5 or whatever. And there are a couple of reasons why magnitude estimation might be interesting. One is that it leads to a ratio scale as opposed to an ordinal scale. And so in theory, a ratio scale supports all mathematical operations and parametric statistical analysis. That means we can, for example, validly calculate things like the mean, whereas for an ordinal scale, purists might argue that that shouldn't be done because ordinal scales only support the counting of values and equality or directional relationships. Whereas to calculate a mean, you also need to use addition and subtraction, which in theory, ordinal scales shouldn't be used for because the quantities are only relative, not specifically defined. In the specific context of relevance or complex concepts like these, magnitude estimation measurements might also give other benefits. First of all, the granularity of the scale is just chosen by the rater. So we don't need to decide in advance, are we going to have a 4-level scale or a 101-level scale? And secondly, judges can't run out of categories. So for magnitude estimation, in theory, you can always choose a bigger number, or conversely, you can always choose a smaller number because fractional numbers are allowed. So conversely, for an ordinal scale, suppose you see what you think is a really good document and you put it in the highest bucket, such as highly relevant on the 4-level scale. Later on, if you see an even better document, the only thing you can do is put it into that same highest bucket, right? You can't assign a high number, whereas magnitude estimation, in theory at least, allows us to get around this kind of limit. So a group of us were interested in exploring magnitude estimation and relevance scales more broadly, and this is work and some results I'm going to report on that was done with people who are in the session today. So this is collaboration with Eddie Maddalena, Stefano Mizero, Kevin Reuterow, and Andrew Turpin, and this was a series of studies carried out over a number of years. This isn't an information retrieval conference. I'm just going to try to outline it at a high level and talk broadly about the results from a crowdsourcing aspect. So we used a test collection. It's called the Trek 8 test collection. Essentially, Trek is a yearly event that provides a test bed for people to evaluate search systems. So in essence, what we were doing is evaluating search systems over a collection of newswire documents and based on a representative set of 18 search topics or queries. And the reason we use this particular test collection is that we have 2 sets of expert judgments available. First of all, Trek itself offers expert judgments made on a binary scale. And secondly, Eero Sormanen and his team from Finland, who I mentioned earlier, for this same test collection, they had already gone and done expert assessments on a 4-level scale, right? So we have 2 different expert assessments on 2 different scales. And what we were then interested in doing over this progressive work was to test how this can be done by crowdsourcing. We wanted to explore different ordinal scales. So we got judgments on a binary scale, a 4-level scale, and a 101-level scale. And we also tried out this magnitude estimation process, so an unbounded scale. And turning to the crowdsourcing task then, this proceeded as follows. So first, a participant had to read task instructions, and then they could provide consent if they were willing to continue, or otherwise they could leave the experiment. And just to note, this study did have ethics review and was approved as being ethical. And then the second step for the magnitude estimation scale, because people are likely to be less familiar with that, they had to successfully complete a training task. The training task was based on the estimation of line lengths, but in essence, it was similar to what we just did together earlier. So this was also our first quality check. So people had to successfully assign numbers to the line lengths in terms of relative, for a shorter line, they should have a lower number than for a longer line. And if they didn't pass that quality check, they couldn't continue. We then required them to read a search topic statement or an information need, and then they were presented with a simple multiple choice question about that. And so this was our second quality check. They had to answer this correctly to see, to demonstrate that they were paying attention and able to understand the task. For the main activity then, the participants had to judge a set of 8 documents, presented one at a time in response to that information needs statement. Each batch of documents consisted of 8 items or 8 documents, And they were constructed by selecting 6 documents randomly from our large collection of documents. And we also put in 2 special documents which had existing expert judgments at the extreme levels. So a expert judged not relevant and an expert judged highly relevant. And this gave us our 3rd quality check. In other words, we could check if the workers were successfully identifying that the highly relevant item should get a better score than the non-relevant item, whichever scale they were using. And finally, we had a 4th quality check, which was based on time. So participants had to spend at least 20 seconds on 6 of the 8 documents, right? So to avoid them just randomly clicking through. So what happened? Here are some scale comparisons. And again, I'm just going to try to convey, hopefully, the intuition of what's going on here. I'm only showing 2 of the 4 scales. On the left is our 101 level scale, and on the right is the magnitude estimation scale. And these graphs are relating the crowdsourced scales to the 2 expert scales. So let's look at the left panel first. If we look at the first 2 columns on the left, these show the distribution of our obtained values on the 101 level scale split by the binary expert judgments. And you'll see that the x-axis labels are N for non-relevant and R for relevant. Yep. So we're splitting our crowd worker received judgments on the 101 level scale by whether Trek expert assessors said it's relevant or not relevant. The next 4 columns are similar, except here we're breaking down our 101 level crowd worker responses by the Sormanen 4-level expert scale. So remember, these were going from left to right: non-relevant, marginally relevant, relevant, and highly relevant. So, all right, these boxes have nice colors and dots and boxes. The boxes are, as usual, summarizing the 50% core distribution of values. The horizontal black line is the median. The whiskers show the range, and some dots are outliers. The takeaway message is the boxes are going from low to high, both for the binary and also for the 4-level scale. Okay, and this is what we would expect to see if we were getting sensible signals in general from our crowd workers. Okay? So the crowd level scores, assigned scores, align with the direction in which the experts assigned things. So these trends look promising. We can also try to more formally assess that, and I think that I'm starting to run short of time, so I'll try to speed up. We can also look at external and internal agreement. So external agreement is the agreement between assessors and a ground truth. So this is a more formal way of quantifying what we saw in those previous graphs and sort of visually noticed that it seems sensible. A widely used approach for external agreement is to calculate what's called pairwise agreement. So you take all possible pairs of documents and you check if an expert said document A is higher than document B, does the crowd rating on whatever scale also say that document A is higher than document B? If it is, you have an agreement. If it's not, you have a disagreement. And overall, the external agreement was pretty high. It was around 0.9 to 0.95 for the binary Trek expert judgments and around 0.75 to 0.8 for the Sormanen judgments. We also considered internal agreement. That's sometimes called inter-rater agreement. So in other words, this is asking how much do the crowd judges agree with each other, never mind the external judgments for the moment, for the internal agreement. This was slightly more tricky. So there are a lot of approaches in the literature. And again, some of the people who are in this session today have worked on this extensively. But some famous measures that you've probably all come across include things like Cohen's kappa and its extension Fleiss's kappa. We used a quantity called Krippendorff's alpha, which is another example of a chance-corrected measure of consistency. Krippendorff's alpha, in theory, allows for some sparsity in the observations. So one of the challenges for crowdsourced work is that usually, unlike in traditional experimental setups, we don't have necessarily the same person providing responses across everything, right? So remember, our tasks were batches of 8 documents, but that means across the collection of the whole, even though we have 10 responses for each document, it's not the same 10 workers who've judged everything. Whereas these internal agreement measures pretty much assume that in how they're set up. So Speeding up even more, just for your information, here is what happened with those internal agreement measures. This is Krippendorff's alpha. The green lines, again, on the left is the 101 level scale. On the right is the magnitude estimation scale. The green lines are the agreement overall. Along the x-axis are the individual search topics. And then the blue and orange lines further split this out by agreement on non-relevant expert marked items, the blue line, and relevant expert marked items, the orange line. And so what we can see is internal agreement seems to be kind of stable, although it's lower for magnitude estimation than for the 101 level scale. And moreover, the blue line, so agreement on non-relevant items, tends to be higher than for relevant items. And this, again, sort of reflects what we might have expected to see, because typically people can very quickly agree when something is not relevant, right? You can say, oh, well, this is rubbish, but it's harder to reach agreement for relevant items, the orange line. So very quickly, the summary then is it's feasible to crowdsource reliable relevance judgments using various different ordinal scales or even a weird magnitude estimation scale. It's important to use appropriate checks to avoid noisy data. So we had a number of things here: a training task, understanding or attention questions, sanity check against unambiguous examples, that's often called gold tests in the literature, and minimum time requirements. It's useful to check both internal and external agreement, although, as noted, internal agreement is a bit tricky to apply in the crowdsourcing concept. And another side observation, it's not necessary, even if you have a large ordinal scale, such as our 101 level scale, you don't really have to define every single level. People seem to do quite well if you just label the endpoints and let them choose on a number line. So that's all from me. Hopefully we still have time for a moment or two of questions. If you're interested in these topics, please email me. And if you're interested in the data sets, well, the latest publication that this was based on, there are the details. Thank you.